Alright, let's not be too crazy here. I know we just got a rate equation that even biologists tend to use to model population growth, and even, I don't know, anything that grows on itself grows exponentially. So scientists might use one thing that I know we use a lot is bacteria growth in a petri dish. If the petri dish doesn't, was infinite basically, where the bacteria could keep on growing on itself, then you'd expect an exponential kind of curve. And you can guess what an exponential looks like. Bam! That's what it looks like. Though it should be noted that if you went back in time, you'd have less and less and less and less, because it only grows when you increase time. So this is what your graph basically looks like for this guy, no matter what your rate is. I mean, as long as your rate is positive. You could have negative percent growth. That'd mean losing a certain percentage exponentially. But this is one of the finest formulas of mathematics. But even simpler is this formula, which Euler took a gander at. E to the x. As simple as that. If I'm at this x value, what y value am I getting, or what time am I getting, whatever. I guess you would make x time in this case to make it this formula. Then you change the rate. But he wanted to go further into this. And by the way, sorry, I forgot to go over this. We start out with the formula p times 1 plus our rate to the time. But we slowly realized that giving us an amount was less exact. And so we replaced this with e to the r. That's e with a certain rate, t, p. So it really stems naturally from our original banking definition of interest. Growth does. G of t. Alright, I only bring that up because I never went into why I made that leap. But it wasn't a very crazy leap, I don't think. Alright, so now that we've found a way to split things up many times, what else can we say about this wonderful number e? So 1 plus 1 over x, the x power. As you take x going to infinity, this number approaches the number e, Euler's constant, or the natural number. So here, let's talk about something that feels entirely different for a second. I didn't have to rip that off, but I did. So here's something that we did in early 1600s. We're going back in time for a second to what we call the logarithm. Alright, this was the discovery of the logarithm. In fact, it's the discovery of the natural logarithm, which we'll get into. But first, let's just talk about this curve. So, in early 1600s, this guy named John Napier, or is it Napier? I think if it's British, it would be Napier, but I think it was French, so I'll say Napier, but yeah, let's say Napier, just to be inexact. But in I'm going to say 1613 or something like that. Either way, early 1600s. Let's say early. This guy named John Napier. I'll write his name. John Napier. I think saying it that way makes it easier to spell than Napier, but whatever. So, John Napier basically wrote down what a logarithm is. And all he did during this time period, at pretty much the same time, maybe slightly earlier, Rene Descartes wrote down Cartesian equations, ways to relate a y variable to an x variable. And so we thought about it, and this guy, John Napier, only had to investigate, instead of saying y equals x, give me a straight line like this, I'll put a dashed line, which just means every value on that line is when y is equal to x. Well, this guy investigated what is the plot of x times y equal 1. look like. Which means that if I have two lengths of, let's say, a rectangle, x this direction and y in this direction. If you saw my video on 0 and 1, you've seen this already. But this is a way to look at it more analytically, and so you can get cooler results. Either way, so x and y, and let's say the area is always 1. So that means if I stretch x, it's going to get longer. Then y is also going to have to get shorter because we still have an area of 1. And so you can continue this pattern. If you stretch it more, it's going to have to get thinner in the y-axis until you get infinitely long. So you can actually connect the dots here and actually put it on our graph, because these are actually the x and y values of our curve that we're looking for until it gets infinitely long. And so this curve, it's actually a little steeper when it gets closer to 0. Looks like this. This was the curve he investigated. Now today we'd write it y equals 1 over x because we like y and x being on opposite sides. The argument to be made is that it's easier to plug in this equation than this equation, because this equation leaves out a step. If I plugged in x equals 5, then I'd have to do algebra to solve for our y value. Whereas this just tells me that if x is equal to 5, that's 1/5. Done. Gets rid of that extra step. But still, I like it this way. So that means this is our curve y equals 1 over x, or x times y equals 1. The curve where, yeah. And you can expect equaling 1 is a very special value, because when things multiply to 1, that's basically the perfect version. And realize this rectangle thing is always true. If you measure from 0 to this point, it's always going to be the same area. John Napier did what we call today, I believe, quadrature, which is literally putting shapes, quadrilaterals and stuff like that, onto a grid to approximate the area at certain points. So it is kind of just a little bit of fun. So if you draw an accurate graph of 1 over x, it's the harmonic function, well, whatever, I'm not getting into that. Then if you take the area from John basically asked a different kind of question. Then this, we always know that plotting a line like this will give us an area of 1. That's acceptable. But what he questioned was, if I started on a certain point on the graph and measured an area to the bottom of it, what is the area? Again, this is basically what he asked. I mean, of course he has his own, oh shoot, I got ink on myself. I shouldn't have colored that in. Whatever. He had his own specific thoughts in mind, but this is how I think of it during that time period. So, interesting enough, starting from 1 is very logical. So starting from 1, 1 on your curve. And he would just ask, hey, if I went to any value x, what is the area here? So turns out it is ln of x, also known as log base e of x. What is a logarithm? Well, it's actually inverse of an exponential. Let's graph an exponential, because we have all these graphs that we can do. An exponential is less than 1 at this value, and then at 0 it's 1. Anything to 0 power is 1. Then at 1 it is equal to e. 1 it is equal to e. And then it grows bigger and bigger. At 2 it's equal to e squared. And e squared is basically 3 times 3, so it's slightly less than 9. Yeah, it just gets bigger and bigger. Now, the inverse operation is the operation where, let's say we had the function e to the t, so we had 100% growth, all right? Growth at that time. If we went at this backwards, if you ask the question, hey, not at this time, what is my growth? If I have this growth, what is my time? That graph will look a lot like this. In fact, it will look like a reflection of this, because it gives you the exact same values, just you're changing what you use for x and y. So you get a curve that looks like this. And it gets pretty flat because this gets big fast. This gets big fast, so it goes to a really tall slope fast, whereas this gets small fast, so it gets to a really flat slope fast. And so if you look at this, this is a map of actually the area of this curve. And this is the inverse. This is, if I plug in the growth, so ln of my growth is my time, also log base e. That tells me e to the power of my logarithm gives me x. E to what power? E to the n power is x. That's what that tells me. E to the n is x. That's so you can read a logarithm. Now, natural logarithm is used so much that in high school you write ln instead. In fact, on a calculator, you're going to find ln. I was about to show you, but I don't think I need to. Now, does this make sense? The area from 1 to x on the curve 1 over x is this curve, this logarithm. Let's plot. Area from 1 to 1 is 0, just like it says. Area from 1 to e to what power is e? Well, e to the first power. E to anything to itself is itself. So if we go over to e, then we're going to get 1 for our area. And interesting enough, this area is exactly 1. So it would have to be e as a curve. But even further, the further you went, the less area you gain. Is it's going to go up less and less for that value. So if you're at k, it's going to only go up to ln k. So the area becomes less and less. And I'm sketching area on here. Technically it's not the area, it's exactly the value at each point. So the value at e tells me the area here. The value at k tells me the area here. So the value, if you go high enough, becomes less and less and less. So those points match up, the areas at least, from 1 to that value. Now even more so, if you measure areas backwards, technically you get negative values. And this value gets taller and taller, so the area goes to infinity. So if you follow this, this area goes to negative infinity because you're measuring areas backwards from 1 to, let's say, 0.5. That is ln of 0.5. Logic goes onward forever, and it goes to negative infinity. This is one of the most prime examples of why it's the natural number. This is a very simple curve. It's just saying x times y equal to 1. Sorry about that burp. Wow. But yeah, this is a very natural kind of function. And so by just measuring the area, you get the inverse of the natural growth function, which should blow you away. So John Napier made huge tables of these exponents, of these logarithms. If I'm at this value, how much is this area? But it took us until Euler. Euler was our dude. It was Leonhard Euler. I think I did a video. Maybe I didn't yet. Leonhard Euler, who realized that e to the, let's say t, that's your growth, is actually inverse of ln, or logarithm base e. I should write it both ways. You should get used to both. In college, I believe, oftentimes you'll see log of g, meaning log base e. It's implied. But it turns out that's not really the case, because, in high school, it's not really the case, because usually it's implied 10, which is not the case later on, especially in real mathematics. Either way, I digress. So log base e or ln, or in college or actual math texts, we just use the term log because it's so useful of an equation and so interesting, I would say. So there's a lot of papers using it. So either way, it took Leonhard Euler in 1750. Remember, John Napier started out in basically 1600, so that's about 150 flippin' years for us to realize these functions were flips, or inverses of each other. They told us the same info, plugging in different values. I thought that was interesting. But that is part of the reason why we give the number e Euler's number. Now, as you'll discover later on, e has other special things. Like, it is this function. I mean, it can be represented as inverse factorials from 0 to infinity. Just add it all up. If you don't know what that means, that just means 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. Oops, 1 over 2 factorial. 1 over 3 factorial, so forth. If you did that to infinity, that is actually equal to e. In fact, it gets to e faster than the other way found, 1 over 1 plus 1 over x to the x power. This goes to e slower than this does. You only need a few terms of this for it to get close to 2.71828, which is neat. Continuing on. So, but you'll find out, if you don't know what a factorial is, you can look at other videos, you can look it up. It's really easy. It's 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 8 factorial is 8 times 7 times 6 times 5, whatever, going down. That's factorials. And you write with an exclamation mark. Whatever. Again, I digress. This is just side info. This info, Euler discovered this summation. And a summation is just a infinite addition. Honestly, you should look at my videos of summation, because summation is amazingly simple, yet it can get amazingly interesting and complicated just by including things like this e fact. Whatever. I think we're getting this okay. We'll probably investigate that e business later. I think I already did it once, but I didn't do it in this much detail. Thanks for watching, and just get used to this idea of a logarithm. And also, logarithm looks like an entirely different notation than e to the x, because that doesn't say e to the x in this form. It says log base e of x is n. Or, if you're used to an exponential form, e to the n power is x. So x is now the growth. I like writing it this way. E to the t is growth. Logarithm of growth is time. E to the time is growth. Yeah, whatever. You can take this even further if you wish. Goes everywhere. Anything else? I think we're done here. Yeah. Thanks for watching.